being here in person, giving the seminar, and the floor is yours.
Thank you. So it's such a pleasure to be here in person, my first in-person talk after the pandemic. So I'm very, very excited to see you all. Today I want to talk to you about some simulations, but mainly about the synthetic observation. So I hope I get to explain everything properly of the magnetized ISM, the series of simulations of isolated galaxies that I started in 2017 when I was still in Crete, and I still do right now at the Scuola Normale. This is my list of collaborators. This is mainly work I have done with Costadino Stasis and Vincent Pellegrin in Crete. So let's see, how does that move forward? Okay, like this. This is my typical introduction slide, so maybe let's not see myself again. Galaxies are magnetized, probably you all know that. And how do we know that? We know from various observational traces. So here I've used this very nice figure of the same galaxy. This is M51, as was published with a very nice recent work. I was very happy to be a part of it by Alejandro Serrano Borlaf. You see in these watery traces on top of the optical image of the galaxy, these lines represent the magnetic field as is traced here in the far infrared polarization and here in radio polarization. Now, in far infrared polarization, we trace the magnetic field through its interaction with, through the dust interaction with it. So what happens is you have elongated dust grains, they spin for whatever reasons, and the fact that they are elongated causes the light to be polarized as it passes through them, right? So then you see the polarization, the far infrared, that gives you the plane of the sky, magnetic field in this case. The radio polarization is due to synchrotron. You have very energetic cosmic ray particles that gyrate in the magnetic field of the galaxy and give you, again, the plane of the sky magnetic field, but as you can see here, it's traced differently. So this is how we know in general that galaxies are magnetized from radio polarization studies, mainly from far infrared. Recently, this is with Sophia Hock Plus. With also Faraday rotation. Faraday rotation is the phenomenon that the plane of polarization of radiation rotates as the radiation passes through an ionized plasma. So by the angle, the change in angle of the polarization plane, we can measure the line of sight magnetic field in the hot component. So Faraday rotation can also give us some information on the magnetic field of galaxies. The Zeeman effect, I listed it here as a tracer of the magnetic field, but Zeeman effect is a splitting of the lines due to the presence of the magnetic field, but you can do this only very close by regions and with very long integration times. And so it's not really a tracer for galaxies, it's more for molecular clouds or even the diffuse ISM very locally. So what do we know from all of this? We know that galaxies are magnetized. We know that they have large-scale coherent fields, as you can see, especially from this image here, you see, the magnetic field has a large-scale pattern and an organization. Less so here, but we can come back to this later on. And from equipartition arguments, because all you know is the plane of the sky angle of polarization, you can guess also the strength of the magnetic field. So by this equipartition arguments, we know, and also from some Faraday rotation, we know that galaxies host magnetic fields of a few micro Gauss. And this is important because a few micro Gauss is roughly in equipartition with the turbulent energy of the galaxies and the thermal energy of the galaxies. So it's dynamically important. Magnetic field plays a role in the dynamics of the galaxy. The first estimates also for redshifts 1 and 2, tentative detections, show that these magnetic field strengths were already present at that time. So the magnetic field plays a role for a large portion of the galaxy's life. Oh, no? So of course, the Milky Way is no exception, and it's kind of harder to know the morphology of the magnetic field inside the galaxy for the same reasons we don't know the rest of the morphology because we're sitting inside. But the Planck satellite did a very good work at mapping the magnetic field as a foreground to what it was actually looking for. So this is a map with the same kind of Van Gogh pattern on top of the image. This is a dust intensity map overlaid with the plane of the sky direction of the magnetic field as we see it from within the galaxy. And this is in 353 gigahertz. This is where I took this map from. You can see all nice images on this website. And this is what we know from the dust polarization. We know that the magnetic field is dynamically important. Yes, the magnetic field is dynamically important because it tends to align with the density structures where the column density is low. So if the density structures tend to align with the magnetic field, it means that they know the magnetic field is there. Magnetic field controls the turbulence to a large degree. And this is the map as we see in Faraday rotation towards very distant sources. That's why it's so patchy here. So people go and look at very distant sources and they see the Faraday rotation in the distance between us and the source. And then we can guess at what the magnetic field looks like from its line of sight component. And you can see kind of a quadruple structure on large scales. These tiny little things are H2 regions because the Faraday rotation also depends on the number of electrons. So H2 regions stand up. Right, so galaxies are magnetized, the magnetic field seems to be strong enough to have an effect. What does this mean? Well, the magnetic field acts in two ways if, on the fluid, right? If you remember from your plasma dynamics, the grad pressure term that you get from the magnetic field has two components. One is kind of like a pressure, the fact that the magnetic field resists compression, and the other is the tension. So what does this mean? It means that magnetic field can delay the formation of dense gas because it adds to the pressure. So you cannot compress very much in certain regions. Thermal instability is affected. So the classical picture of the ISM condensing into a dense phase, the cold neutral medium, and a less dense phase, the warm neutral medium, is not so clear-cut anymore because there is an additional pressure that prevents the condensation. The magnetization also affects the behavior of turbulence because there is an anisotropy there. Unless your magnetic field is completely isotropically turbulent, if it has a mean component, as we saw it does on large scales, it will introduce an anisotropy. This means that the turbulent motions of the gas will also be anisotropic. And this has important implications for the formation, again, of small clumplets that can lead to stars, the shape of molecular clouds, the fragmentation of molecular clouds, and the whole star formation process. And on the large scales, it has been proposed for a long time that the magnetic field can control where molecular clouds form. This is called the Parker instability. So imagine the galactic disk and imagine a magnetic field that is toroidal, so it's parallel to the disk everywhere. You have two forces there. You have gravity that tends to pull everything towards the disk, and you have buoyancy. So when you have supernova explosions that insert thermal energy, cosmic rays, things tend to go away from the disk. What does this do to the magnetic field? It bends the lines. And then you have the role of tension. So the lines become pinched towards the disk in certain locations. And where they are pinched, they help the compression. So you can form GMCs, giant molecular clouds, where the magnetic field permits it. So it's very important to study how the magnetic field affects the evolution of the galaxy through all these complex mechanisms that I mentioned, and how then the evolution of the galaxy affects the shape and the strength of the magnetic field. So what do we do in order to study this? Well, what I do is run simulations. The simulations I will present today all share a common idea behind them in the setup. These are run with the Ramses code. The Ramses code has this very nice characteristic that it can treat a collisionless component like dark matter or stars and connect it to the hydrodynamical, magneto-hydrodynamical component through the Poisson equation. So in this series of simulations, what I have done is set, with the help of Monte Carlo selection code called DICE, set up various distributions, initial distributions for my collisionless components and for my gas. The collisionless component that takes most of the mass for these galaxies, which I want to be Milky Way-like, Milky Way mass, so 10 to the 12 solar masses in total, is the dark matter halo, right? So we have an NFW profile. This is a typical density distribution for a dark matter halo that is concentrated in the middle. That makes up for 98.5% of the total mass. Then a stellar disk that is set up as an exponential disk with inverse hyperbolic cosine in the z direction. That makes up between 1.4 and 4% of the total mass. Then a very, very light gas disk, which in the code is treated on a grid. So the collisionless component is treated as really large particles that interact gravitationally with each other and with the gas. The gas is sampled on a grid. So you have a Eulerian approach to solving the hydro-MHD equations. And then on this, we have a toroidal or poloidal magnetic field. Toroidal circles parallel to the disk, poloidal, sort of like a dipole. So you have donuts-like lines going around this. And the magnetic field is said to be very strong at the center and exponentially dropping with height and with radial distance from the center in the disk. Right. So this is the first kind of setup I'm going to talk about. I did back in 2018, which is with imposed spiral arms. So on top of everything that I said before, on all of the galaxies, I have imposed the potential of spiral arms. I was too young to know that they can make the spiral arms by themselves. So this starts off with spiral arms. These are the two setups for the magnetic field I was showing you. This is the initial condition. So here you see the disk with its spiral arms right from the beginning, toroidal and poloidal magnetic field. And this is a list of the models. Probably you don't see them very clearly. So some of them have FB in front. This stands for feedback. Means that we create new sterile particles where certain criteria are satisfied. And then these stellar particles, the new ones, after a certain time, explode as supernova. So they give thermal energy back to the gas. These ones are the set that doesn't have feedback. This is a control set without feedback. Then this B here stands for the plasma beta. So this is a central magnetic field strength, actually. So it's very low, as you can see. And the topology and all the four models is toroidal and two are poloidal. Just to see what happens very early on. So this is the disk with the vectors that show the magnetic field after only 30 mega years. So like one star formation cycle, if you want, of the galaxy. And already you see that the models with feedback, so here are two models with feedback. This is the initially colloidal, initially toroidal. This is a strong magnetic field. This is a weaker magnetic field. The models with feedback already show a very irregular, almost random structure of the magnetic field. This distance here, this box that I'm showing, is about 25 kiloparsecs. So up to very large heights above and below the disk, we have this randomization of the magnetic field. Here is the control runs of the same simulations without feedback. So you see here at the center where there has been some rotation, you see there is randomization already, but the rest of the magnetic field seems to maintain a lot of its initial structure. So now in these simulations, we had a numerical problem that prevented us to evolve them for very long. So the time steps became very, very, very small because the advance speed up here, out here is very big. The density is so low, the magnetic field is moderate. So the code could not cope with this kind of immense advance speed. Now we have solved that problem, and I will show you simulations that run for longer later on. But this is already interesting because what we saw, these are the power spectra, what we saw about this randomization, we had to quantify a little bit. So here I'm showing you on the left, the magnetic field power spectra, and on the right, the kinetic energy power spectra. The reddish colors, pink, brown, and magenta, pink, and brown and pink. Sorry for the color scheme. Just to show you that they all go together more or less. They are the ones with feedback. And the colder, like cyan, green, and blue, are the ones without feedback. So, and this is the black is the initial toroidal, and the gray is the initial colloidal, initial conditions. So there's two things to notice here. The runs with feedback at large scales, so low wave numbers, change behavior, so they diverge from the initial condition. And two of them also in small scales. The colloidal ones lag, they know the initial condition better, even better than the toroidal. And this is because of the mass loading of the lines. So as the galaxy tries to rotate, the tension I was saying is greater with the colloidal field because it's almost vertical in this configuration. This is the kinetic energy. So here the cut is clear. You have runs with feedback, runs without feedback, the initial condition, and the runs with feedback. This is the Kolmogorov slope, which means isotropic turbulence. The runs with feedback, they know up to very large scales that there is feedback. There is a turbulence that establishes itself immediately, while the runs without feedback only grow in very small scales, and here they just follow the initial condition distribution. Something is not clear, please interrupt me.
Can I
yes,
ask?
Of course.
I think I missed which kind of feedback you refer to.
It's only supernova feedback. Yeah. So a second set of simulations, I call them Amalthea because I was hoping to get a lot out of them. It's a Cretan myth about horn of abundance that keeps giving, right? So here I've used a similar setup, but without imposing the arms. And we made some changes in the setup and in the approach of the mesh, mesh refinement in the code that allowed us to run the simulations for longer without running into the time step problem. So here I have 4 models Model M is our canonical model designed to see if the magnetic field has a long-term evolution. It has feedback, a supernova feedback as before. W has a much weaker magnetic field, but is otherwise identical to model M. M no feedback is the canonical without feedback, and MLR is low resolution. So we gave up one level of refinement of the grid. And here's the time evolution of this model in two cases. This is the M no feedback, so the canonical model without feedback. This is with feedback. And this is the density I'm showing here with the some magnetic field lines. So you see that there is no big difference between the two, because there is the randomness of the field lines. But in this model, what in this long time evolution, you see we reach 1.5 and then 2 gigayears. This randomization of the field happens anyway because of the differential rotation of the galaxy. So both models eventually have a similar behavior in terms of their magnetic field. What is nice here is that the galaxy forms a central bar at 0.5 gigayears. See what happens when you don't impose anything. So the galaxy may decide to make a bar. The magnetic energy that I'm showing here is amplified by a factor of 100 over the same time scale. You see, this is the W, this is the weak magnetic field. These are all the other runs I presented, so they all achieve the same factor of magnification of the magnetic field, but this low resolution starts to diffuse. Feedback and no feedback follow more or less the same trend in terms of strength of the magnetic field. So what we wanted to know then is, were we actually successful in saying a galactic dynamo here? So who knows here what is a galactic dynamo? I get to write. No, I don't get to write. This is nothing. So I can explain to you. Right. So magnetic fields in the universe, especially of the strengths that we observe right now, are not very easy to explain. If we go back to cosmological times, there are some mechanisms that can create a magnetic field out of an unmagnetized universe, but they are super small. They are between 10 and 15 orders of magnitude lower than what we observe right now. So many theories have been proposed to explain why we have such strong magnetic fields. One of them is a dynamo. What happens in a dynamo? You have a transformation of kinetic energy into magnetic energy. You move a fluid, you have a V cross B term in your evolution equation. So you transfer through this term energy from motion to magnetic field. You can generate a magnetic field. In a galaxy, there are two mechanisms that have been proposed that can transform kinetic into magnetic energy. One is a small scale mechanism. The turbulent motions that reorder the magnetic field. This reordering leads to reconnection. The magnetic field changes configuration, but at the same time grows. Right? So there's certain motions that can do this, that can help grow the magnetic field, others that cannot. There's a huge literature on this. But one is turbulent motions, small scale rearrangement of the magnetic field. The other is large scale motions, differential rotation. And this is what we were suspecting here. Differential rotation takes magnetic field, winds it up, and at some point, this winding will not be able to continue anymore. The magnetic field will reconfigure itself from a toroidal component to a poloidal. So it will reconnect, make a poloidal component. Same thing, poloidal component from supernova explosions, whatever force of buoyancy rises up, twists, and then reconnects. So you can create one component from the other continuously. And this is what I try to see here. So I try to follow magnetic field lines from one snapshot of the simulation to the next and see if I can see this rising up of loops, which I did here, above and below the disc. You see this twisting that then reconnects, will reconnect. And this winding, if you see the green line up there, it's winding up very closely in the center. So the mechanics of the dynamo were there. And then what we want to look for is also the morphology predicted by dynamo is there. But this is a prediction. This is the shape of a dynamo created field from an analytical model from Sticks in 1975. And here you see the projection of the magnetic field lines on the plane of the disk. So you see here the poloidal component of the field in these contours. So we want to do the same thing. Let's see how it looks like if we contour the magnetic field on a projection, cut the disk in the middle, and take the mean component of the field. So we passed a filter throughout the galaxy. We filtered out the fluctuations, that would be the turbulent component, so as to see the large scale component, the mean component. And this is what we got. So this is when using an 8-cell kernel, and this is with a 16-cell kernel. So if I put on top this contour again, we kind of get the same shape on the larger scales. So we were kind of convinced that it's a dynamo. Then we ran many more tests that I will not bore you with. But we did find that there is a mean field dynamo in this setup. In the end, though, we were left with many open questions. So this is the first part of the talk. What did we learn from these models in terms of the evolution? We found that in these multi-physics simulations with cooling, the stellar component, dark matter component, feedback, we did observe a rapid randomization of the fields. We saw that there is an inherent instability of the initial magnetic field, even without feedback on the smaller scales. And in longer evolution simulations, we saw that there is an amplification of the magnetic field by a factor of, by a factor of 10 and 500 megayears. Is this enough? It's not. So it was very nice to see this mechanism in action, but we saw it stop also. You remember these lines plateauing at this factor 100. But I also told you that we need orders of magnitude, not just one order of magnitude. We need several orders of magnitude amplification. So we're still missing something in these models. And this is what I have here in red. What is the role of the small scale turbulence? Did we model it properly? Probably not. We need this small scale dynamo that I was talking about. So we also saw that this time scale for amplification coincided with the formation of the central bar, and would be great to see if this is a persistent characteristic in this kind of simulation. Is this the initial motion that drives the amplification? We create a dynamical feature, at the same time the magnetic field follows this evolution, and then it reaches this strength and stops. Finally, how does this compare, all of this, what we found, compared to what people see in observations? Did we get something right, apart from getting something close to the theoretical prediction for the dynamo? And this brings me to the second part of the talk, where I'm gonna go through a little bit of synthetic observations that we start to do with these models. So here I need to go back to this Planck map that I showed you. This is this is the attempt well, you know, Planck tried to measure the cosmological beam modes. Some of you may be familiar with what the cosmological beam modes are. But this is a signal of the inflation during the early times when the universe supposedly went through an accelerated phase of expansion. The fact that an observer had an horizon in front of them created a background of gravitational waves that would be emitted by this horizon towards the observer. So this is a stochastic background of gravitational waves that would induce a signal of polarization that is dominated by what is called B modes. So what is a B mode? When you have a vector field to decompose, you have many options to decompose your vector field. This is one of them. This is a basis of this decomposition that is a curl-free, the E mode, and a curl-bearing component. And it has the advantage that it doesn't depend on your choice of direction. You can always decompose into these two modes. And then this has the advantage of making a reliable analysis in angular power spectrum. So the Planck satellite went off to find a signal in the whole sky angular power spectra of these cosmological beam modes. Thing is, signal is dominated by our own galaxy, by the polarization of the dust I was talking about. So for people like me who care about the properties of the interstellar medium, especially of our galaxy, this is a great fortune because we could learn a lot about this further. So what is this analysis, especially of the 353 gigahertz, where the dust polarization from our galaxy is particularly dominant? What did we learn from this? We learned that the power in the E mode polarization is about twice that of the B modes. Interesting. The E modes show a positive correlation with the total intensity. Very interesting as well. And the origin of both these trends has been theorized to be the alignment or misalignment of density structures with the magnetic field. And there is a very, very big literature on this as well. So what we wanted to see now that we have all these galaxy models is, do these correlations change based on our position of the galaxy? Now we have many positions to choose from. And also, what can we learn about the morphology of the magnetic field that the observer lives in from this type of correlations? So what did we do? We took these first models that I showed you with the imposed arms, and we placed an observer all around the disk at a distance of 8 kiloparsecs from the center to imitate sort of our position in the galaxy. And here I show you the column density of the gas, the total column density of the gas, and some indicative positions of the stars show all the positions of the triangle. So we had 72 viewpoints per galaxy. And then for each viewpoint, we create a set of maps in what are called Stokes parameters. These are the actual parameters that are measured when one is measuring polarization. And this is what we get. This is the total intensity of the dust, and this is the Q parameter and the U parameter. These two are used to reconstruct the polarization vector, this direction of the magnetic field I was talking about. Then what we did with these maps is mask out the disk. This is what was done in the Planck analysis to see the sort of unbiased picture of the magnetic of the power spectrum. This is how we did this. How we passed from the simulation to this. We took an observer inside, shot rays all over the sky using hill peaks to distribute our sky in pixels. And this is the equations that gave us the Stokes parameters based on the parameters of the simulation. We had to assume a dust temperature, emission as a black body from each cell. And then we took all of these realizations with the masking levels, different levels of removing the disk, and turned them into power spectrum. Let me show you how this, yes, of course.
Yeah, so the dust distribution is from your simulation.
Yes, we assume a constant dust to gas ratio all over the galaxy. And we turn that into, we assume that dust has the same temperature everywhere. So, because otherwise we would need radiative transfer that we don't have.
And you assume a constant efficiency for the dust.
Yes, perfect efficiency. Yeah, perfect alignment. We tried actually to mimic the misalignment with density, but it didn't make a huge difference because then we masked the disk where this is the most important effect. So this is what a tour around the galaxy looks like in dust intensity. You see that the sky looks very different from different positions around the disk. And you may also be noticing that some of the maps have a separating line in the middle or some crosses around. These are artifacts from passing Cartesian grid to a spherical grid. And these are removed in our approach, are removed in the power spectrum level. So we filter out the very large scales and the very small scales to get rid of this noisy square pattern. Right, so we have the maps, we have the power spectra, like was done in the Planck analysis. How do we quantify the correlations between them? These are two parameters that quantify these correlations I was telling you before. This is the REB that measures the ratio of the power of E modes over D modes. And this is the parameter I will be calling RT, because we care about the cross correlation between the E modes and the intensity. Remember, if it's 1, it's perfect correlation. If it's -1, a perfect anti-correlation. If it's 0, there is no correlation. Right, and this is the plane of parameters that we got from all the maps, all the models, all the masking levels in RT, this one, and REB. So this one is what Planck measured. This is the maximum likelihood from our models. But you see, our models are all over the place. You can get practically any combination. The fact that the maximum is close to what Planck found is not a very important thing that we found. We had to find it because it means that the magnetic field and the density know about each other. They are correlated in a way. This is the basis of the theory of the MHD evolution. So this one, the thing that gives us a perfect anti-correlation between the dust intensity and the modes, is the poloidal run. Remember, the one with the vertical almost lines without feedback. And this is to be expected. You have a magnetic field that is almost always like this, with a density that's perpendicular to it. So perfect anti-correlation, this is what we find here. Right, so we sort of made this first test, that the sanity check, that our parameters cover a reasonable space, parameter space. Let's see if we get some correlations with the model or with the other aspects of the setup. So here there's histograms of the REB and RT. On top are the models with supernova feedback, and the bottom are models without feedback. So right from the start, we see that the feedback has the effect of narrowing down the range of the RT and REB. This is what you see here. If you compare this to this, you see this distribution is much more narrow. Here also, but to a lesser degree for RT. Also, we see that the toroidal magnetic field topology leads to positive T correlation, and that the stronger magnetic field, this is this T, I cannot even read it on this. This is a strong field, strengthens the correlation. So the stronger the magnetic field, the stronger the RT correlation. This is a trade-off we found. And this is already interesting. It means that in these parameters, there is sort of a signature of the large-scale behavior of the field. Then what we did is see if there is a correlation of these parameters with the position of the observer in the galaxy. This phi angle here shows you where the azimuthal angle of the position of the galaxy. So it's like we opened up the map, like the map with the stars that I showed you. So here's the position, and here is the dust intensity. This REB and RT. And the gray bands show you where the spiral arms are. So of course, the dust intensity knows where the spiral arms are, but to a statistically measurable degree, so do REB and RTE. So this we did a Kolmogorov-Smirnov test to verify this, that the observers in spiral arms are a peculiar sample. They are more correlated to each other than to the general population, sorry. And the same is true of observers inside superbubbles. So as we maybe know, we are inside a bubble, in a low density bubble in the ISM. So we said, well, maybe some of these correlations are because we are seeing the whole world inside this bubble and it has a surface with a surface magnetic field. Let's go and check that. So we went and picked superbubbles by hand from these simulations. We put observers in there and then compared this sample to the general sample. And it turns out that observers inside superbubbles are also a peculiar sample. So they are more similar to each other than to the general sample. And this is sort of where I can leave you with this study. So we found that there is a clear dependence of the power spectral characteristics on the galactic model, which is very interesting. Especially the presence of feedback makes a very big difference. But the effect of the observer's position dominates all of that. So it's sort of disappointing if this persists, because it means that we will sort of never know if the trends that we observe from our position are just because we are here and the spread is huge around these values. But still, we found no dependence of this RT and REB behavior with the mean magnetic field or with the mean density of the gas at the position of the observer. So this means that it's not the absolute values around us that matter, is the correlation between these quantities and the complexity of the ISM around us that makes our position special. So yeah, as the last sentence, we need new galaxy simulations with a stronger field, more realistic feedback, maybe also chemical tracers or a dust tracer to be able to continue with the synthetic observations. So hopefully next time I'm here, I'm gonna tell you more about that. Thank you.
Thank you, Eva. That was a very interesting, very nice talk. Now it's time for questions. If anybody from the chat wants to ask questions, please write them in the chat. In the meantime, are there any questions from the audience? Oh, quite a few. Okay, so let's start from the back. Daniele?
Yeah, very nice.
Thanks.
About the first part, the simulation. Do you know if the large scale amplification is related to MRI or not?
Sorry, Eva, before replying, can you repeat the question so that the people from Zoom
Yeah,
can?
so Daniela was asking if the large-scale amplification of the field could be due to MRI. So this is a thing that I did consider, especially since we saw this randomization of the field in the first setup. But I don't know of a way that I can investigate the growth, the nonlinear growth of the MRI, or even the linear growth of the MRI here. So because it's not clean, we would need a cleaner setup to see the characteristic wavy pattern of the MRI. But this is a very interesting suggestion. Yeah.
More questions?
Hi. Very nice. I wonder concerning the first part of the talk, what strategy do you have in mind to check the amplification at the smaller scale, just like increasing the resolution or increase the
So the question is if at the simulation part, we are considering any mechanism to treat the small scale dynamo. And the answer is that yes. So one thing that we found that is a weakness of this approach and is brand new, so don't hold me very accountable on this. I don't really know if this is the case, but that the stars formation scheme, the fact that we take some gas away and we form a collisionless particle in its place, may be robbing some magnetic pressure from the high density regions. So this is one effect that we are studying right now with a student of mine, but that cannot be the end of the story. So we are introducing radiative feedback from the stars to see if by boosting the energy at the small scales, we can recover the small scale dynamo. And of course, high resolution would not hurt either. Yes.
More questions, Leo?
To what extent is equipartition embedded into your simulation? And if not, or even if it is embedded, to what extent is equipartition validated by any sort of observation?
Right. So the question is, to what extent equipartition is embedded in the simulation, and to what extent equipartition is observationally valid, right? So, right. So in observational terms, equipartition is kind of built in the assumption that we can guess that the magnetic field is dynamically important whenever we can measure it directly, like with Zeeman splitting. We know that it's strong enough to be in equipartition. But on the galaxy level, you are right to pose this question, because many times, no, most of the times, we assume equipartition in order to estimate the magnetic field strength. And even when people do David-Chandrasekhar Fermi, they assume equipartition to some extent. So we don't know if this is actually the case. We know from Faraday rotation that this may be the case. So we have an estimate of the magnetic field strength from Faraday rotation that is also to the strong side. Now, in the simulations, equipartition is not built in. Actually, we start with a magnetic field that is so weak, it's almost embarrassing to compare to Milky Way models because it never grows to equipartition values. But now again, with the new corrections to the algorithm and to the setup, we can go for a magnetic field that is much stronger. And yeah, I hope we can resolve also this in terms of the observational signatures.
Yes, I have a question. You know this relationship between the magnetic field strength with density,
right?
And interstellar medium, where at the low densities, the magnetic field strength is basically constant. It doesn't change with density. And then when you get to the molecular cloud level, it starts to increase with a power law of about 0.6 more or less. There's a total debate about that. So do you find this trend in your simulations?
Right. So the question is about the correlation, the observed correlation between density and magnetic field. So the density in the interstellar medium, well, the magnetic field in the interstellar medium, whenever it can be measured, seems to have a flat behavior with density at low densities and the parallel behavior at high densities. So the question was if I find this in the simulations. And disappointingly, we find something that is compatible with everything. So with any slope. So there is a blob covering all the magnetic field values. Like
So you mean
can I
there
do?
is out of dispersion?
It's a huge dispersion of the values. But even the observational relation, I'm not sure where the break is, and if you shift things right and left, there's a huge debate, you know. But
Yeah, there is out of upper limits.
yeah, so I can advertise our review now. There's Patel et al. 2022 Protostellars and Planets chapter. We have a long discussion about this, but in these simulations, we don't see a clear correlation. It's all over the place. Yeah, unfortunately.
There are no questions in the chat. Is there any other question in the audience? I have one myself. Yeah. So you saw that a bar was formed when you let the spiral arms evolve on their own. Did you see any dependence on the magnetic field strength or shape, colloidal, toroidal?
Yeah, I forgot to say that in this long-term evolution, I only tried the toroidal because the colloidal, because of the mass weight of the lines, is nightmarish. But no, there was no dependence on the magnetic field. But what we found, and I cannot explain it still, is that if you have the same simulation without magnetic field at all, the central bar rotates with a different frequency. No idea why. It still forms. They form together, but at later times, one is like this, one is like this.
Interesting.
Super interesting. So, and it's not magnetic braking because I tried it. So if anyone has ideas and wants to discuss about this, we can.
Awesome. Okay, last chance for asking questions. If not, let's thank Eva again for this excellent talk.